So hello everyone, today's tutorial we're going to design a full adder. We're going to use the previously made gates that we did in the previous tutorials. We did the AND, the NAND, the NOR and the inverter. Using those gates we can make the AND and the OR and the XOR. So I basically started them, so they're simply how can I show it? Yes, okay. Test. Where is it? Yeah, there. So you just open cell, you click on, for example, the NAND gate, you place it, and then you place an inverter, for example. Let me zoom out a bit. Okay, to see the insides of the layout, you can just press on the eye again here, then you can see everything. You can start connecting the elements together and formulate your new gate. This will be simple, so I'm going to skip it. What you need to do is, for example, in my case I'm doing an AND 2 gate. It's basically an AND 2 followed by an inverter. Okay, so I think I can just make one so that we're all at the same track. Okay, so to begin with, what we need to do is okay, go here. We need to place this. No, this pad is already. Let me try to get an output. Okay, so as you can see, we have different metal layers. The first metal layer is the blue one, then followed by the purple one. Each metal layer is placed at a different Z height, if you might say. So they won't intersect with each other, even if they look like they're intersecting. They're not in real life because they'll be placed in 3D. As you can see here, the pink wire is underneath the blue connection, and this is not an intersection in any way. So just to illustrate my point. Okay, so first of all I need to connect the VDDs together. So this is the first, and the ground as well. Then I need to take a wire out from both A and B and the output. Then I need to take a wire out from the output of the NAND and feed it into the input of the inverter. Now, as you can see, it's in a blue wire. It's preferred that you use the second type of the metal. To do so, I'm going to place a metal 2 pad and connect it to the input of the inverter. Place it on top of it. I can bring them a bit closer now. Okay. Now, sorry. Okay. I think. Oh, okay. Now it's fine. Okay. Now I'm going to go through it and connect it to the output of the NAND. Oh, okay. To choose this first, and hopefully yes, it's fine. Press F5 each once in a while to see if we have anything wrong. What is this? Okay, this was extra. And the rest? Oh, okay, those are too close to each other. So just bring it a bit down, and I think. Okay. So try not to connect wires that are close to each other, because you'll have crosstalk, and there are some rules that are set by the program, and it'll tell you anyways. Okay, again, it's fine. Now what we need to do is put some pins so that they'll help us use those cells in bigger formations. you want to do a complicated design later on. And I think this is the output. Yes, it is. So I'll place this pad over here, a metal 2 pad, and connect it here. Oh, yes, you have to choose the metal 2 wiring. Okay, sorry. Okay, so you have to press Control to go through the pads and the wire. Just be careful on what are you pressing. Okay, here I'm going to name my inputs A and B. Doing this because it will help me later on implement the full ladder. So increase the size a bit, and then the arc or the wire itself needs to be named. This will be called small a and small b. By doing so, I'm creating something similar to a pointer. So this wire will be referenced by which is the same thing. So this wire is the same thing as this wire. Okay, let me call it this B just to be consistent with the actual design. You can do whatever you want, it's fine. This is increase the size a bit. Okay, same thing here. This is A, and then this will be A, and increase the size. Now this interconnection, we don't need to do anything with it. Here, we just need one. Here we need the output. It will be simply A ANDed with B. And you need to name the arc as well with a small A and B. And then the output arc should be the same, and B. You can choose to ignore this step, but you will find some trouble later on. Since I also connected the VDD and grounds, I also need to place a pad. This will also help in the interconnections later on. So let's name them. This will be my VDD, and this is my ground. Then you need to name the arc itself, small VDD and small GND. Oh, I think, is it? No, it's not. Okay. I think I named, well, when the name is not in the middle, then you're naming a new node, and we don't want to do this. Okay, let me increase the font size, because you normally need to see it later on. Okay, this is wrong as well. So this is VDD. Yeah, I think. Okay. Make it 5? No. I think I was yeah, this is. This should be 5. Okay, cool. Now the last step is that we need to name this net. This is VDD. Just any one of them will suffice. And this is GND. Just to tell the simulator where to connect each part. Okay, so this concludes the design of the AND gate. You can do the same thing for the OR gate. Just replace this cell with an OR gate, and then rename the outputs. It's totally the same. To help me in the design, I also created the Xor Gate. And okay, let me try this before I continue. Okay, let's delete this name, and name, and connect the actual thing. no errors, and yeah, it's fine. Let's do this, it's better. Okay. Okay, so this is my XOR gate. Now the XOR consists, okay, this is the logic diagram of the XOR. It's simply A naught ANDed with B, ORed with A ANDed with B naught. You don't need to design this, you just need to worry about the layout. It's made out of cells, the same concept. The only problem is that you need to connect the VDD and ground planes, ground rails of each gate together. To do so, I used the third metal layer for the interconnections between the inputs and the outputs. I used the second input, the second metal layer, which is the purple one, and simply that's it. As you can see, that they are black boxes. You don't need to worry about the inside layout and stick diagrams. That's it. If you need to see what is inside, just press on the eye, and it's so that you can relate. But it's not that important. Again, you need to make A and B as references, and then refer to them. It's easier. Not only easier. I think it's the only way that you can do it. Here I have B inverted ANDed with A, then A inverted ANDed with B. All of them are ORed together, and I'm getting the output here. And let me see, yes, okay. Yeah, and the ground rails are all connected, I think. Only this one is not. And yes, to simulate it, you can use this spice code. I'm going to copy it into my archive. Okay, cool. Just delete it. And then this is my OR gate, my AND gate. Let's start with the full adder. The full adder schematics are, sorry, not this one. Yeah, it is this one. So this is a simple full adder. It's A ANDed with B, ORed with A ANDed with C, ORed with B ANDed with C. And since I have only two input OR, I'm using two OR gates. And this is for the sum. The carryout needs an A XORed with B XORed with C. This is it. So where was it? Okay, let's start. So to begin with, we need the AND gates. Where is the AND gate? Okay, I think it was there. Okay. Copy it 3 times. Okay, as you can see, the inputs and outputs are clearly labeled. It will be now easier to interconnect them and use them in your design. Let me try put them this way. Maybe connecting them to VDD will be easier. Now I need the OR gate. I think I'll need 2 since I have 3 inputs to the OR gate. And for the carryout, I will need two XORs actually. As you can see, the XOR is the biggest of them all. Okay. And this is an XOR. See? Black boxes. This, if you want to see it, it's in here. You can press it again to see what's inside, and press it again to see what's inside the inside. So that's fine. Okay. So to begin with, let's see if we can be ANDed, and then here. It's very troublesome. So okay, so to find somewhat of an optimum solution to the interconnections between the VDD, the inputs, the outputs, you need to do you need to use what we learned in class, which is floor planning. Now you need to draw some diagrams on paper and then try different scenarios. In my case, I think I'm going to use this diagram. Okay, it will be like this. Okay, so VDD will only go right, and ground will go left. Okay, and I need to put it a bit down. The smaller it is, the better for the overall IC size. And then we need to connect the VDDs together, or sorry, grounds. Pull this up a bit, pull this up a bit more. Okay. This is my GND here, and as you can see, my ground is going to the left only, whereas my VDD used to go to the right. They should not intersect because they are of the same metal layer, and intersecting is very bad. Let's try a 5. Okay, everything's fine. Now, okay, this is okay. So as always, I need to specify inputs and outputs. This is an input. Okay, so this one will be my A, and this one will be my B. Let me zoom in a bit because I can't see them. If you press shift, you can choose different elements at the same time. So this will be small a and this will be small b. I don't really care about those for now, or the sizes, so it will be simply like this. Okay. Oh, we need C as well. I know I shouldn't copy it, but I need to change the name of this arc now. This will be C. Okay, so here we'll have our C. And the size is 10 again. Okay, so here we have A, here we have B, here we have A ended with C, and then here we have B ended with C. Then for the outputs, okay, see they're intersecting, but it's fine here. So, oh, what's happened? Okay, let's try 5. We have an error. Where is it? This is too close. Okay. So let's delete this wire and try it again. Try to segment your wire, it'll be easier. Okay. Here. And then this output here. Okay, I think I can compact them a bit. Oh, this is bad. Press shift on this wire again, but why? Type, it's fine. If we were to use this cell in another design, it'll be tedious if it was really big. So it's better made smaller. Okay, now this output is actually my summation. Let me get a bit bigger so that you can see it. Okay, now what we need to do is interconnect those. What do we have here? Yeah, this is our Xor gates. Where is the... okay, it's fine. Oh yeah, I didn't press F5. Okay, it's fine. Always remember to press F5 and save, since something, in case something might happen, because this program is a bit buggy and you don't want to lose your work. Okay. Oh no, here, yes, we have it. Yeah. Okay, so this will be my A, XOR'd with B, XOR'd with C. Let's see now. And this will be my C out. C out. Will be size 10. One last thing we need to do is, oh yeah, we need to connect VDD so that it's common for all gates, and ground as well. Okay, we don't care about anything that are not of the same color. So yes, okay. So here we need to state that this is our VDD, and over there we need to state that this is our GND. Press F5 and always check for ERC well check. This will make sure that your VDD and GND are connected to all the gates. Okay, so the last thing we need to do is test. You need to go to MISC, place a spice code, make it bigger, multi-line, size 10. Okay, here first of all we need to see the sum. Sorry. Then we need to add a new input, since we have 3 inputs here. It's C, and let's make it 0 DC5. Okay, so A is is our variable. It's changing from 0 to 1. Let's make our B 5 and C 0. So the sum should be 0 and the carryout should be 1. Using this simulator, I think you can only have one load at each. You can test each output individually. So after we finish with the sum, we're going to test the C out. Okay. Oh yeah, I think I made a major mistake. Let me check. This is C out. My apologies. And this is our sum. The same thing goes for the layout. We don't need to change everything, just the outputs, the labels. This is the sum. Okay, no problem. Let me change. This is my C out. Okay, everything's fine. Change the size to 20 so that you can see it. Wow. Still small. Press Ctrl 9. Okay. Wow, everything is very small. I think you need to enlarge it so that you can see it when you take a screenshot or something. Okay, I think we can deal with these things later. Let's try to slow down. Okay, so what we had is A is rising to 1 while B is always at VDD at 5 and C is always 0. So 1 plus 1 should give us 0 and carry out 1. Now we saw that the summation is falling because in the beginning we had B, as I said, B was 1. When A went to 1, summation went down. And let's see if we can see the C out. Yes, it is correct. So the C out is 1 because 1 plus 1 we have a 0 and carry out 1, so it is correct. Let's try a different combination just to make sure of our design. Maybe put C to 5 volts and yeah. So in this case both summation and C out should give us a logic high. C out and sum. Yes, this is correct. So congratulations, you just finished your full adder. Thank you, and you just, if you want, you can do some minor adjustments to the sizes and the structure of the design. Thank you. So just the last thing you can do is 3D window so that you can see your design in 3D. Let's hope it opens soon. Oh, it didn't. Okay. Yes. So basically, with the left mouse you can go up and down. With the wheel you can zoom in and out. As you can see, those are the different metal layers. This is a side view. Let's see if I can zoom in to see here. See, the purple wires are not at the same level of the yellow ones. Same thing goes for the blue ones. So this helps a lot in the integration of circuits. And let's see, this is the full design of the full adder. So that's it. have fun and enjoy.